All right, everybody, let's take a look at rational functions, which what we've got is a very special kind of equation that's going on. I'm gonna use a little bit of terminology we've already used. So we've got f of x equals n of x divided by d of x, where n of x is the numerator and d of x is the denominator. And you see those are both functions. And in fact, um, your book defines these as polynomials. So not just any old function, okay, but they got to be polynomials. So if you remember, those are non-negative exponents. So it's going to be like x to the fifth plus x to the third plus whatever. Not negative, not they can be zero. X to the zero is a 1. That's okay. And the coefficients are all going to be real numbers, right? So you can't have 4i or something like that. You can't have 3i as a coefficient. They've all got to be real numbers. But the coefficients can be fractions and decimals and stuff like that. Okay, and then there's one more piece of information that goes with this, and we should all know what it looks like. This d is a function, and it's on the bottom, and we're saying this whole thing is a function, which means d cannot be equal to 0, right? We can't divide by 0. We already know that. That's what makes bad spots in the domain. So, in fact, we're going to have some special words this time that are going to deal with that. So, these graphs are going to look interesting compared to what we've already seen. So, the graphs are going to look like pieces. Okay, and there's lots of different ways that they can look, but basically, we'll have our x and our y, and somewhere in here, we're probably going to say, hey, there's a vertical asymptote. Okay, we'll talk about what that is, but maybe there's a horizontal asymptote. The idea is the actual piece of the graph is going to look something like this. There's a part down there, there's a part up there, something like that. Or maybe both parts are on the bottom, or maybe both parts are on the top. But you'll have a couple of pieces going on that we'll deal with. Or, even more in depth, sometimes there will be two vertical asymptotes, okay? And think of those vertical asymptotes as those are the spaces that are dividing up my graph. So maybe I've got a part over there. Maybe I've got some piece right here in the middle, and maybe there's a part over there. Okay, so in this case, because I have two vertical asymptotes, I would have three pieces to my graph. In this case, I only put in one vertical asymptote and I have two pieces to the graph. So it's important to note that the asymptotes that I'm drawing there, notice that they're dotted lines, right? Those are not parts of the graph, okay? They are actually lines that are going to segregate our graph apart, okay? So that's I'm gonna use to separate into different pieces. But the actual dotted line is not a part of the graph. It's just a really important piece that we want to talk about, okay? So we will talk about, okay, find the vertical asymptote, find the horizontal asymptote. That's not the actual graph of the function, right? Because for instance, this is a vertical line, and if that was part of the actual graph of the function, a vertical line can't be a function, right? So it would knock me out, basically, out of the function world. This piece here and this piece here, that's the actual graph of the function. But I need to know where those asymptotes are because I need to know where the pieces are separated at. Okay. And different things can happen. The tops can both be on top. The pieces here can both be on bottom. Sorry, not the tops are on top. The pieces are on top. The pieces can be on bottom. They can be opposite. One can be on top. One can be on the bottom. When I have three pieces like this piece in the middle can be an S curve like this. If you remember your functions of graphs, this is a cubic, right? Okay, so they can look like that. It could be a negative cubic coming down like this, or this could look like a parabola. Oh, excuse me, here in the middle, it could look like a parabola. It could be an upward facing parabola. So different things can happen. This is just a generic idea of, hey, what do these graphs look like? And the important part is that we know that they're going to come in pieces. Okay, so I'm using a couple of words here, and I'm using them pretty liberally, right? So one is vertical asymptote, and Um, I don't expect you to know this necessarily, but it is an algebra concept. So, vertical asymptote, I will almost always shorten that to VA just because mathematicians are lazy and we like to abbreviate things. That's where variables come from. Okay, so vertical asymptotes. And what this is I'm going to put an S there. These are lines that are given by bad spots, let's say that are determined by bad spots in the domain. And I've used that phrase before, right? These are bad spots in the domain. Okay. So if you'll remember, the bad spots in domain happen whenever I divide by 0 or whenever I take the square root of a negative number, right? Those are the things that I've got to watch out for. And usually, because we're dealing with rational functions here, right? Usually, what we're going to be worried about, because this is a fraction, is that the bottom here can't be 0, right? The function on the bottom cannot be equal to 0. So in this case, I'm worried about dividing by 0. That's what I'm looking for. Okay. So recall, we can't divide by 0. At least not until you get up into about calculus 3, and then we have weird situations that we deal with, but for our purposes, we're gonna say you can't divide by 0. Okay, so those are gonna be, things that I'm worried about, and the bad spots in the domain, the thing to remember here is that when we find these vertical isotopes, we are never, ever gonna cross them. Never, ever going to cross a vertical isotope. And the reason for that, you don't hear me say never, and you certainly don't normally hear me say never ever. Those are very rarely will I use those in a classroom, but we're never going to cross a vertical isotope. And the reason why is because these are bad spots in the domain. If I had them, I would have a spot where I cannot graph. And so that is not part of the function, basically. If that spot was in there, I wouldn't have a function. All right. So let's look and see what this looks like. We've done some of this before when we were dealing with functions and stuff like that. F of x equals, here's my example, f of x equals 3x over x squared minus 4. Okay, so we're going to look at this thing and we're going to do a couple of pieces real quickly. The first one is we're going to find the domain. You've been doing that. We did that at the beginning of this semester. And then we're going to find the vertical isotopes, right? Okay. So, and basically what I hope you realize when I do this is that these are basically the same thing. Okay. Finding the domain and finding vertical isotopes, you are basically performing the same exact math. Okay. So A says, find the domain. Okay. Well, if you'll remember, we can't divide by 0, so we're going to pull out this denominator, pull it down here, and say x squared minus 4 cannot be equal to 0 because I know I can't divide by 0, right? Okay, so x could be 0. 0 squared minus 4, I'd have a negative 4 in there. That would be okay. But the whole entire thing, that's why you see me pull that whole entire denominator, x squared minus 4, that guy can't be equal to 0. Okay, and then I say solve real quickly for the x. We've done this since like the first day. Add your 4. X squared can't be equal to a 4. And then I want just x, not x squared. So everybody knows I'm going to take the square root of both sides. And when I do that, I need that plus or minus in there, right? So x cannot be plus or minus, and we know the square root of 4 is 2, right? Okay. So that's your domain, and remember that that tells you what the bad spots are, and I know I use that word a lot. It's a very Webster word. It's not in probably many textbooks, but it's your bad spots, and that's at x equals 2 and x equals -2. So for instance, if I plug 2 in here, 3 times 2 on top, that's a 6. That's not a problem. But 2 squared is 4. 4 minus 4 is 0. If I plugged in a 2, I'd have 6 divided by 0. And again, if you punch that on your calculator, let me just pull that out. 6 divided by 0, you're going to get an error. So let's see what our calculator tells us. Sometimes people believe the calculator more than they believe me. So 6 divided by 0, and this is a more updated software system, so it actually even says error divide by 0, so it even knows exactly what I did wrong, right? And so you can quit or you can go to, but the point being you cannot divide by 0. That's a bad thing, that's a bad spot in my domain, and I can't do it. Okay, so we find the domain because we're looking to see, hey, where are my trouble spots, right? What's gonna cause me issues? Okay, but what we see is the vertical isotopes part B here. We've actually already done it. X equals 2 and x equals -2 are my vertical isotopes. Okay, so what does that mean? That means that there are two, notice it's x equals 2 and x equals -2. Those are vertical lines, right? Vertical isotope means a vertical line that we're not going to cross. That's what we said. We're never going to cross these vertical isotopes. Never, ever. Remember, I don't say that often. Okay, never ever crossing a vertical isotope. So what this means is we're going to come over here to x equals 2, and we're looking for the vertical line that goes through x equals 2. Well, it's here, but it's also here, right? And it's also here. And it's also here. It's also down here. So any spot where x equals 2, that gives me a vertical isotope. And so like this could be this point 2, +5. This could be 2, -3. All of those points are on the line x equals 2. Okay. And the same thing over here at -2. X equals -2, y equals 10. Okay. X equals -2, y equals 0. X equals -2, y equals -4. All those points are on that line. So there are 2 vertical isotopes in this problem, and that's what it looks like. Okay. And this is the beginnings of the graph. We're not finished yet. I'll come back to that and finish it. But that's the idea behind vertical isotopes. Okay. So hold this thought and we're going to come back to it. Okay. I'm going to actually set this paper right to the side so I can pick it right back up. But we're going to talk about horizontal isotopes real quickly. Okay. So here's the thing about horizontal isotopes. When you see a horizontal isotope, what we say is those are horizontal lines, right? That you might be able to touch in the middle. It does happen occasionally, not normally in this class, but you might see something where it crosses in the middle. Um, but then never, and I'm saying that again, in the end behavior. Okay, so what the heck does that mean in behavior? I think I've talked just a tiny bit about it, like whenever we talk about a parabola, okay, here it's going up and to the right, here it's going up and to the left. That's what's happening as we get toward the end of the x-axis, either side, either on the positive side or on the negative side. Okay, so what we're talking about here is what is happening way out toward positive infinity, way out toward negative infinity. So here was our graph. And what we want to know is as I come way out here toward this x equals infinity, right? Positive infinity is way out there. Negative infinity is way out there. What I want to know is what's going on over here as I get really close to positive infinity. What's happening to the y values? Okay. And if you remember or you know from way back, a horizontal line looks like y equals some number, right? Okay. Vertical lines, I didn't put it there, but let me go back here to the vertical isotopes. Vertical isotopes are x equals some number. Okay. So what we're saying is if I came way out here to infinity, what's the y value doing? Okay. Is it shooting up towards positive infinity? Is it shooting down towards negative infinity? Is it getting really close to some number in the middle, which we'll see that happens a lot? Um, Same thing out here towards negative infinity. Is the graph suddenly shooting up? Is the graph suddenly shooting down? Is it staying close to a particular number? What's going on with that? Okay. So, what we see is that these isotopes cause the graph to follow a certain type of behavior. Okay. So, like the graphs I showed you at the beginning, do you notice that as the graph gets close to these isotopes, it gets closer and closer and closer, closer and closer and closer? Here's a horizontal isotope. It's getting really close, really close. I tell my students that these isotopes act like magnets to these graphs. Okay. So this guy's going to get really close to this vertical isotope. And even here in the middle, see how it crossed right there in the middle? Okay. That we're going to find out there's a horizontal isotope in there, but it crossed right there in the middle. Okay. But here, as I get farther out, closer to positive infinity, look what it's doing. It's coming up right against that isotope. What's happening here? It's coming way out up against that isotope. Okay, so isotopes are going to act like they're magnets. Okay, that's what we're going to see. All right, so what the heck's going on here with these horizontal isotopes? That's what we would like to know, right? Okay, so there's actually 3 different things that can happen with horizontal isotopes. That's why I kind of started a new page. I'll come back to that graph in a second. But 3 different things can happen with horizontal isotopes. One is that we're looking at equations. So remember, some f of x equals some function, and there's a top and there's a bottom, right? Okay. So there's 3 things that can happen. Normally, we'll see something like x squared plus 5x minus 22. Okay. That is a polynomial, and technically, I could write it over 1. And 1 is a polynomial, right? So it's a boring polynomial, but it's still a polynomial. So here I've got something divided by something, and but I can look at it and say, okay, this is technically a rational function. That's not one that we would normally deal with, but I'm just trying to make my point here. What's going on in this equation, in this function? Well, it looks like a parabola, right? Okay. And it's not coming close to any particular horizontal isotope or anything like that. In fact, whenever we graphed parabolas, we just graphed them, right? We didn't have to worry about anything pulling it one way or the other. Okay, so what's really happening here, if you'll remember, I've said multiple times, 1 is the same as x to the 0. Okay. So, the leading terms almost always win whenever we're dealing with stuff. Okay. And what I mean by win is there's kind of a little bit of a tug of war going on here that's causing this thing to graph like a parabola. If I had an x to the third, it would look like this, an S curve, if not a lot was going on, but it could look like that, right? That's a really big S curve. And it goes in 1, 2, 3 directions. That's x to the third, right? This was x to the second. And how much this thing bounces around in the middle or how much it's flat is determined by the stuff that's going on back here. Okay. That causes it to bounce more or whatever. We'll get more into that later. Okay. But the shape of the graph is determined by this. Okay. X squared is the largest has the largest exponent in this top, and that's what forces this guy to be a parabola. It's not a cubic. If it was a cubic, it'd have an x to the third in there, right? This guy's going to look like a parabola. Okay. The idea here being there's also a tug of war going on between the top and the bottom. Okay. And again, the term with the highest power wins. Okay. So in this case, the term on the highest power is on top, right? 2x squared. The exponent is bigger than the exponent on x to the 0, which is a 0, right? Okay. So literally what we're going to do is we are going to compare our exponents. Compare the exponent on the top to the exponent on the bottom. Okay. And of course, these are the leading terms. We're not, I actually, a lot of times, whenever I teach this in algebra class, I'll be like, okay, this guy wins. And so we don't even care what's going on back there. So, yeah, this is going to cause it to bounce around a lot. But the end behavior is determined by that first term, right? Whether it's a parabola that opens up or opens down, there could be positives and negatives back here, but what matters is the first term, right? That leading coefficient, this guy's positive, so this is an upward parabola. If there was a negative out here, it would be a downward parabola, and it would not matter if everything else was positive. The first term wins, okay, in that tug of war. So that's what's going on here. So you compare the top, the coefficient on the top to the, I'm sorry, you compare the exponent on the top to the exponent on the bottom, and you just try to see which one is bigger. That's all you want to know. That's what we're after. Okay. And what we already see is when it's bigger on the top, we don't have an asymptote at all, right? It's just a regular old parabola or a regular old cubic or something like that. So there's actually 3 rules here whenever I deal with horizontal asymptotes. And I didn't say it earlier, but of course I'm going to abbreviate this HA. Sorry about that. Kind of looks like ha. Okay. So 3 rules about horizontal asymptotes. I'll write it out this time. 3 rules. Okay. Number 1, if the exponent on top, the largest exponent, let me actually make it official. If the largest exponent on top is bigger than the largest exponent on bottom, then there is no horizontal asymptote. Okay. And we usually will just say, oh, I am so sorry. That's just off the page. Sorry about that, guys. If the largest exponent on top is bigger than the largest exponent on bottom, there is no horizontal asymptote. Okay. And a lot of times it'll just say, is there a horizontal asymptote? And we'll say none. Okay. Easy enough. Okay. That's the case we have whenever we're just dealing with flat out polynomials. And in rational functions, it happens too. So sometimes that's what we're dealing with. Now, is that what we're dealing with in this example that we were working with? No, Dr. Webster. That's what I hear in my head. Okay. What's the exponent on the top? The biggest exponent on the variable is a 1, right? And what about the bottom? The biggest exponent on the variable on the bottom is a 2. Okay. So we're going to literally look at the exponents. This one's a 1. This one's a 2. Is it bigger on top or is it bigger on bottom? Bigger on bottom. That's what I hear. One of my students emailed me the other day and said that She liked it whenever she just giggled whenever I do that, those voices. Sorry, that's what I hear in my head, so you hear it too. Apologize about that. Okay, hopefully it's your entertainment for the day. Okay, so bigger on bottom. So this rule that I just gave you, if the largest exponent is on top, then it doesn't apply here, right? Because that's not this case. So we'll figure it out in just a second. Rule number 2. Okay. What happens if I give you a function and let's just make it kind of nice for this moment. Let's say 3x squared plus 2x over 4x to the fifth minus 4x. Okay, something like that. Okay. And I want you to know what's going on. We're still going to compare the exponents. Okay. So look at the largest exponent on the top. What is it? It's a 2. Okay. What's the largest exponent on the bottom? It's a 5. Okay. So we don't care about this other stuff right now. Okay. We're just going to ignore it. The pieces of this function that are winning the tug of war, on top, it's this first guy, and on bottom, it's this first guy. So it's the x squared versus the x fifth. Which of those is stronger? The guy on bottom is stronger, right? Because it's x to the fifth instead of x squared. Okay, he's got more power on that tug of war. So he's going to win. Okay, that's what's happening here. And let me go ahead and just actually show you what this looks like as when I'm reducing stuff. So it's 3x squared. Ignore that other stuff. We don't care about him right now. Over 4x to the fifth. The 3 and the 4 are going to hang around, right? But what happens is that I can get rid of 2 of these exponents, right? X squared. And what happens? Hopefully you've done some of your exponent review. This becomes x to the third, right? Basically, you can cancel out or reduce out 2 of those with 2 of those. Okay. So what's happening here is that I've got x to the third. It doesn't have to be x to the third. It could just be x to the first. But I've got some x's on the bottom. And when I reduce this, I don't have any x's left over on the top. Okay. So remember what we started out with on horizontal asymptotes. We said, what's happening way out here as I go to infinity? Okay. That's what I want to know. Or negative infinity, either one. So let's think about it. Well, if x was 1, this would just be 3/4, right? That would just be 1 cubed. What if x was 10? What's 10 to the third? Let's get our calculator out. Okay. So, excuse me. I'm so sorry. 10 to the third. It's a 1 with 3 zeros, right? The exponent on a 10 tells me how many zeros. Okay. Times 4 is 4,000. So I didn't go very far towards infinity, right? I did a 1, I had 3/4. Now I'm doing 10 and I've got 4,000. So what's 3 divided by 4,000? It's already giving me this scientific notation junk. So hang on a second while I play with my calculator and make it stop doing that. I think it's under mode. There we go. Okay, so let's say, how many decimals do we want? I want 9 decimals. I'm just trying to force it to stop giving me that scientific notation stuff. Oh, it's still doing it. Well, poo. Okay, so the e to the -4 means that I moved 4 decimal places. It didn't do what I wanted to. Hang on a second. I'll be right back. I'm going to see. All right, I wasn't able to make it. I'm sorry. I don't know why this one won't give me a decimal. It's not very long of a decimal. So anyway, what it's telling me is this is scientific notation. So it would be 4 decimal places that it's moved it. Okay, so it should really be 0.00075, right? So 0.00075. That's what it is. See, they're the same. Okay. I don't know. I tried a couple of different settings and I don't care enough to fix it so it doesn't do that anymore. But it's not that big of a decimal. But look, I had 3/4 a minute ago when I put in a 1. Now I've got 0.00075. What if I went out to 100? 100 cubed. Okay, that's a big number, right? Times 4. Okay, and then I'm going to do 3 divided by, and I'm going to make it do the answer for me. There it is. Now it's 0.7. Okay, 7 of them. So that's 1.0234567. Okay. 0.00000075. Okay, so that's a really tiny decimal, right? I started at 3/4. I haven't even gone very far. I'm only at 100. What about if I went out to 1,000, to 1,000,000, getting really, really, really closer to infinity, right? This is getting really, really small very quickly. So what's happening here is this guy is going toward 0. That's what we're seeing. Okay. So, okay, whenever I have, let me give you the rule. Let me switch papers. I'm sorry. If the largest exponent, here's your example of it, but if the largest exponent on the bottom is bigger than the largest exponent on the top, then there is a horizontal asymptote at y equals 0. Okay, that's what's going on. This number right here, if I plug in 1,000, if I plug in 1,000,000, it's going to get really small and it's going to come closer and closer and closer to 0. So y equals 0 is going to be like a magnet drawing this guy in. Okay, so that's the idea there. That's the second rule. Okay, we haven't talked about this yet, but think about the example. We'll come back to it. It's bigger on bottom. That's what I said, right? So this guy's going to have a horizontal asymptote at y equals 0. Okay. The nice thing about the horizontal asymptote rule is that you're literally just comparing. That's what we said. We're going to compare those two, the top exponent to the bottom exponent, right? So that's pretty nice because it's not craziness, okay? Just compare the exponent on top to the exponent on the bottom. We can see that. We can look at the leading terms and we can figure out which one's bigger, okay? The problem that people have with this one is there's 3 rules, okay? So, bigger on top, so there are sayings, and you can go look them up, Bobo Botton and all that. Bigger on top, there's no horizontal asymptote, okay? I know, weird sayings. If I can remember it, I'll write it for you, but bigger on bottom, there's a horizontal asymptote at y equals 0. Those are the first 2 rules. Okay, there's a third one. It doesn't apply in this particular case, but we'll see some examples in a second. Okay, so let's talk about the third one. What other case haven't we dealt with? We got larger on top. We got larger on bottom. What's the other one? They're not larger on top or bottom, right? They're the same. So rule number 3 is exponent, let me start with largest exponent on top is the same as the largest exponent on bottom. Okay, what do we think's happening here? Let's get an example. F of x equals 3x to the fifth over 4x to the fifth. And again, there can be some other stuff back here. Plus 6x minus 10x. Who cares what that stuff is? Because in the tug of war for the top, the 3x to the fifth guy wins because he's the biggest. And in the tug of war on the bottom, the 4x to the fifth guy wins because he's the biggest, right? And then we get rid of this stuff, and now it's the tug of war between the top and the bottom. So we look between those and we compare those exponents and we say, what are they? Well, the exponent on top is a 5, Dr. Webster, and the exponent on the bottom is also a 5. So they're the same, right? Okay. The largest power on the top is a 5. Largest power on the bottom is a 5. They're the same. Okay. That's this case. That's what's going on. So let's talk about it. What would we do if we were trying to simplify this? I would look at that guy and I'd say, hey, I've got an x to the fifth on the top. I've got an x to the fifth on the bottom. Those will go away, right? So in the long term, not really short, not in the middle, but as I get bigger and bigger, bigger, it doesn't matter what I put in, 1,000, a million, a gazillion, it doesn't matter because those are going to be the same and they're going to basically what we would say, what a lot of people call it, cancel out. Mathematicians call it reducing, right? Okay, so these are going to reduce out and what I get is a horizontal asymptote at y equals 3/4 because these are the same, they go away, okay? So when you have the same exponent on largest exponent on top is the same as largest exponent on the bottom, then if then, okay, this is your example. Sorry, I kind of get messy with this one. Okay, then there is a horizontal asymptote at y equals, and it's the leading coefficient divided by the leading coefficient. Okay, so literally you just look at the number on the top, the coefficient, look at the number on the bottom, that guy's coefficient, and it's literally just whatever it is. So that's, I think, why people don't love the horizontal asymptote rule because there are 3 rules, but really it's really straightforward, right? You're comparing what's on top to what's on bottom exponent wise, and then there's 3 outcomes that happen. And if you kind of remember what's going on in the background, oh, those are going to cancel out or reduce, then maybe it helps you remember them. Those 3 rules you're going to have to know for the first test. Okay, so I'm just letting you know they're going to be on the test for sure. All right, so there's your 3 rules. Let's go back to our example. I'm sorry. So somewhere you've got these horizontal asymptote rules. Okay. I'm sorry. Before I go back to our example, let me throw this in here. Botten. Sorry. Yeah. Botten eats DC. Right? Okay, that's the little saying. You can look it up if you want to. I never quite remember, but I will look at it. I'm pretty sure this is it. Bigger on bottom. This is what we taught when I was in high school. Y equals 0. That's what the 0 is about, right? Bigger on bottom. What do you think this one stands for? Bigger on top, Dr. Webster. Yep, that's what I hear. Okay, bigger on top. What's the N? None, right? What's eats DC? Dang it. I was trying to think of that. E equal. Hang on a second. Okay, see, that's why I don't like these this saying because I don't remember it. Okay, so but I remember now. I had to go look it up. I'm sorry. Eats DC. I was right about the saying. The reason it is exponents are the same. Exponents are the same. And what do you think the DC is? That one I knew. Divide coefficients. And that's your leading coefficients, right? Okay. So I don't really remember it that way, but I know sometimes that helps people. If little mnemonics like that are your thing, then go look it up. It's all over the internet. If you hate that, then just ignore it. Okay. Wipe it from your brain and don't even worry about it. Okay. So our example here, let's come back over here. We've done A, which was find the domain. We've done B, which was vertical asymptote. Okay. I didn't finish writing them all out. We need C, which is the horizontal asymptote. And we need D, which is graph. Okay, so that's where we are. I kind of left off because I was trying to get all of our horizontal asymptote rules in. We know this one's bigger on the bottom, so there's a horizontal asymptote at y equals 0. So I'm going to, I already put that up there earlier, so I'm going to put that's C. Okay, and I'm going to graph this thing. So here's my graph. We've got the two vertical asymptotes. I've got this guy who's a horizontal asymptote at y equals 0, or in other words, the x-axis, right? That's a real common one. It happens a lot that the denominator has a bigger exponent, so we get y equals 0 a lot. Okay. And then I'm looking at it, I'm going, I know because there's two vertical asymptotes. There's going to be a part on the left-hand side. There's going to be one piece over there. There's going to be a piece on the right-hand side, all right, something over here. It's either going to be on top or it's going to be on bottom. And then there's going to be a piece in the middle, okay? So remember that magnet theory, right? Okay, this guy is going to suck up against the magnet. So that's why I say there's only two options over here on the left, for instance. It either does this because it's coming up against this asymptote and it's coming up against that asymptote, or it does this on the bottom. So it's either up here on the top or it's down here on the bottom. I don't know which one it is yet. We'll find out in a minute. Okay. And the same thing over here on the right. Whenever I'm going out here toward infinity, it's either going to do that on the top or it's going to do that on the bottom. And we'll figure it out in just a second. Okay. In the middle, I said before, when I have three pieces, this guy could be an S curve. He could be a negative S curve. It could be an upward facing parabola. It could be a downward facing parabola. But those are only options we have here, really. Okay. It's not going to come up here and bounce around and do weird stuff in there. Because this asymptote, I can cross it in the middle if I need to, but I'm not going to be crossing it 5 times, right? If I cross it, it's going to come up here and just glance through and keep going. Okay. But I'm kind of betting on some parabolas in here. We'll see. All right. How do I know? The truth of the matter is we have to graph old-fashioned in this. Of course, you can use your calculator, and that's fine. I'll show it to you in the calculator in a second. But I've got to kind of graph old-fashioned, and what I'm going to do is I'm going to pick points. Okay. So in between, there's a 0, right? So I'm almost always going to pick x equals 0 if it's one of my options. Okay. On the right-hand side, I could pick 3. I could pick 4. I could pick 5. You could pick 100,000 if you wanted to because it's over here on the right-hand side. It doesn't matter. All I'm looking for, am I going to get a positive number, which puts me above this x-axis? Or am I going to get a negative number that puts me below this x-axis? It's all I care about. And the same thing over here. -3, -4, -5, -500, right? It doesn't matter. All I'm looking for is a point here. And if it's on top, then it's on top. And they're all going to do the same thing. I don't have to check 3 and 4 and 5 and 6. I just check 1 and they're all going to do the same thing. They're all either above it or they're all below it. Okay. remember that as I get out here towards infinity, and it doesn't take very long, 1, 2, 3, 4, 5, I'm just sucking up against this asymptote and I'm not crossing it. The only place we might cross the asymptote, and it doesn't always happen, this horizontal guy, is in the middle. Okay. These verticals, we're never crossing them. Remember, never, never, never. Okay. All right. So let's see. Let's plug in some points. Okay. Let's choose. I'm going to come over here to do my points. My function was f of x equals 3x over x squared minus 4. You can make a t-chart if you want. I don't care. Put your x's and your y's. I'm going to do it just because I can. I'm going to pick 3 because it's on the positive side, -3 because it's on the negative side, and 0 because it's right in the middle. There's 3 pieces, right? 1, 2, 3. So I'm going to pick 3 points. You can pick more if you want to, but you don't need to. So real quickly, let's evaluate this. Put in the 3. 3 times 3 over 3 squared minus 4. Okay, I can get an actual number, 9 over, and this is 9 minus 4. So it's 9/5. But in this case, all I care about is that it's positive, right? Because this is the point. X equals 3, y equals, it's 9/5. That's bigger than 1, but smaller than 2, right? 2 would be 10 over 5. So it's up here somewhere, okay? And again, I don't care where it is. I just, as far as the actual point value, what I care about is that it's positive. So all of this is up here, okay? I'm going to do the -3 next, and it's either going to be here or here. And I will say you get about a 50-50 shot. Half the time it's up above, and there's some stuff going on with the exponent stuff. Half the time it's below. So sometimes these match, sometimes they're opposites. Okay. So you can't just go, oh, it's always going to be whatever. You have to check. And to check, you have to plug in points. So here we go. F of -3 equals 3 times -3 over -3 squared minus 4. Okay. The top is -9. What happened? Oh, sorry, that was -3 squared. What happens when I do -3 squared? That's a negative times a negative, right? So that's going to be positive. So this is still 9 minus 4. So that's still a 5. And this is negative. That's what I cared about. -9/5. Okay. So sure enough, this piece was -3, almost -2, right? -9/5. So he's going to be down there. And where 1 point on this piece of the graph goes, the entire piece of the graph goes. So it's all below, okay? Which means we didn't use that and we didn't use that. We used this one above and this one below. Okay. Unfortunately, in the middle, I'm probably going to have to graph more or pick more than just 1 point because I don't know what's going on. The other thing you could do is you could figure out if there are any x-intercepts here. So we already did x-intercepts before. I'll let you play with that and see. We'll graph it on the calculator in a minute and make sure my graph's correct. But if there were x-intercepts, then I could figure out, oh, this is crossing here and here. Okay, fine. Okay, if there aren't x-intercepts, not any, then that means it's a parabola somewhere going down, right? Okay, so we're going to check. Let's put in the point 0. F of 0 equals 3 times 0. On the bottom is 0 squared minus 4. 3 times 0 is 0. -4 on bottom. Okay. We can't divide by 0, but we can have 0 on top, right? 0 divided by -4 is what? It's a 0, okay? You can do 0 divided by anything, and you will always get a 0. So if you don't believe me, calculator knows all, right? Okay, 0 divided by any number, we're okay with 0 on top. That guy gives me a 0. We can't divide by 0, but we can have 0 on top. So this is okay. This is the 0.00. Okay, I put it up here. My x value is 0. I got a y value of 0. Okay, which tells me that I actually have an x-intercept right there. I'm going to be at 0, 0, which means I still don't know what the heck's going on here. Okay, it could be that it goes like this, and that's like the vertex. Could be that it goes like that. Could be that it goes like that. So I really do have to pick a couple more points, unfortunately. So I'm going to pick 1 and -1 because they're in this middle section. So I need to do a couple more points. Sorry, guys. 1 and -1. Doing this graphing by hand can really be tedious sometimes. So that's why we have graphing calculators. We're going to use them. Don't worry. I'm not going to forbid you from using them. I am going to require you to give me certain pieces of information, like are there x-intercepts? Are there horizontal asymptotes? Is there this? Is there that? And then I'll probably make you give me 2 or 3 points. And then if you use your calculator, it's fine. I'll show you some of the finer points about using your calculator in a second. All right, let's do x equals 1. F of 1 equals 3 times 1, 1 squared minus 4, 3 on the top. 1 squared minus 4 is -3. Again, I really only care that this is negative. Okay, so I put in a +1. I got out a -1. And then because the horizontal asymptote is here, that tells me I put in a +1. I've got a -1 down here. That's a point. And let's do the -1 guy real fast. Okay. F of -1. 3 times -1. -1 squared minus 4. This is -3 on top. Again, remember, -1 squared is a positive. 1 minus 4 is still -3. But look, up above it was a positive divided by negative. Here I've got a negative divided by negative. So negative divided by negative is a +1, right? So I'm going to have the point -1, +1, which is right there. Okay. Now I've got enough. Okay, there's one x-intercept. It's right there. This is a magnet. It's sucking it down. This guy's a magnet, and we can tell it's sucking it up. If you want to plug in more points, like plug in 1.5, you'll get a point down here. -1.5, you'll get a point up there. You can, and it'll help you fill out the shape of this if you want to. But really, I really just need to know, okay, this is an S curve. And in fact, it's that negative S curve, right? It's not climbing, it's going down. Okay, so this is an S curve in there. It's not a parabola. That's what it looks like. Okay. All right, let's see it on the calculator and confirm that I didn't mess anything up. Okay, here I go. Oops, here we go. Y equals, I'm going to delete that. That's from the last video. Okay, I'm going to do 3x. Again, remember your x is right beside your alpha key. If you go to your second and go over and down one, you'll find it 3x divided by, and notice, here it is, sorry. The bottom is x squared minus 4. If I just put x squared here, this calculator is going to do 3x divided by x squared. So I really need to do parentheses, okay? X, again, the x is here, squared. You have 2 options for squared. You can either do what I call the caret or the housetop squared, or you can use this button right here, the square button. It's 1, 2, 3 underneath your alpha button. X squared, and it's minus 4. Okay. And so hopefully whenever I tell this thing to graph, now I remember that the last time I used this calculator, we went down to a -100. So let me switch that real quickly. I'm going to make it -10 again, my window. Okay. Hopefully though, whenever I draft this, I get something very similar to what I've got here. So let's see what it does for me. Okay, There it is. Sure enough, I've got this bottom piece here, I've got the S curve in the middle, and I've got that piece up there. This is a nice, prettier graph than what I've got, but they do match, so I'm happy with that. You could do traces and stuff and follow it and see, oh, my X value is getting really close to 2, but it's not hitting it. And then it skips over to 2.1, and all of a sudden I'm on this other piece, right? So you can do that kind of stuff and play with it. I don't have time to do calculator workshop in this video, but if you've got questions, I would say go find a YouTube video about how to use my TI 83 or 84 to graph. Okay, there's lots of stuff out there. All right. Um, Real quickly, some of you might have something that looks like an asymptote going here, and it looks like an asymptote going there. The reason for that is because let me see if I can make it do it. Mine doesn't even have that option. The reason for that is because sometimes if you have an older software system, so don't freak out if it does that. I don't see it at all. Okay. Older software systems, they will do what they used to call it connected mode. And I don't even see it as an option here. So if you're in a connected mode, basically what your calculator thinks is I've got this point way down here at the bottom, and I need to attach it to this point, the next point I find, which is way up there. And so it'll draw this little it looks like a vertical line or asymptote, but it's not really. Okay. So what you can't do on a test is give me that piece and then that and then that and then that and then that. Okay. If you give me a graph that looks like this, I'm going to know that all you did was punch it on your calculator and you don't really know what's going on. Okay. Because you don't realize that these are vertical asymptotes here and they should be dotted graphs, dotted lines. Okay. So that tells me if I see something like that, I'm going to go, this person just used their calculator and they didn't do the asymptotes at all. Okay. So be careful about that because it's not pretty. Okay. It's not what we're after. All right. That's a really long problem for that. So it's because I was explaining the concepts at the same time we did the problem. We're going to do another problem or two, and they should go faster. Let's see what we got here. Sorry, I'm looking for examples. And going through my notes going, what did I do? Here we go. Let's do this guy. And you're going to tell me if you see vertical asymptotes, and you're going to tell me if you see horizontal asymptotes. So the example, the directions are going to say something like find any vertical asymptotes or horizontal asymptotes. Okay, my math lab is going to say something similar to that as well. Okay, so my f of x equals x cubed minus 4x over x to the fourth minus 16. All right, so let's kick off the vertical asymptotes first, shall we? Okay, remembering that vertical asymptotes are your domain. And so we're going to say x to the fourth minus 16 cannot equal 0. Vertical asymptotes are bad spots in the domain. Here I'm dividing, so I can't divide by 0. So that's how I know that I'm going to write this guy cannot equal 0. I cannot divide by 0 here, right? That's my bad spot. So I got to watch out for those. I got to find them, and I got to make sure we don't use them, okay? So here we go. I'm going to say x to the fourth cannot equal. I'm going to add 16 over. And then here, it's interesting because we're going to do fourth root. So x to the fourth root I'll do this a different way here in a second. Cannot equal plus or minus the fourth root of 16. What is the fourth root of 16? Something times itself, times itself, times itself, times itself, plus or minus because I took the root, right? So 2 times 2 is 4, times 2 is 8, times 2 is 16. So it can't be plus or minus 2. Hey, we had that a minute ago. Okay. If you are looking at this guy going, what in the world? You could have factored it also. X squared plus 4, x squared minus 4 can't equal 0. And then this guy will factor. That's a difference of 2 squares. X squared plus 4 times x plus 2, x minus 2 can't equal 0. So again, if you need to go look at factoring stuff, go look at factoring stuff. Make sure you can do this, and you should be able to factor that pretty quickly, just like I did. Okay. And then you say, well, none of these can equal 0. X plus 2 can't be 0. X minus 2 can't be 0. So here, these x can't be negative 2. X can't be 2. That's what we got, right? Okay. Let's just pick this piece apart real quickly and see what happens. X squared can't be negative 4 because I add or subtract the 4 off, right? What do we think about that? If I square root both sides, can't be plus or minus the square root of negative 4. Hopefully you see it. You might have seen it way up here at x squared plus 4. The thing is, anytime I make x squared plus 4 equal to 0, those are positive things, right? I'm not going to find a value like I do down here that's going to give me x squared. Whether if I square a positive, it's a positive, right? If I square a negative, it's a positive. So I'm not going to get anything like this unless not in the real numbers, right? What do I have to do here? Unless I go into imaginary, plus or minus 2i, right? We'll talk a little bit more about 2i later, or I in general. So what we see here is the only way that this guy, x squared plus 4, I have a solution is if I go into imaginary numbers, and we're talking about real numbers here, right? We're not talking about imaginary numbers. So we don't care about that. Okay. So vertical asymptotes, 2 and negative 2. They're not always 2 and negative 2. I'll make sure to find us one in a minute that doesn't have that. And then what about, come back up here, horizontal asymptotes. We don't care about this. We don't care about that. We care about the x to the third. We care about the x to the fourth. Those guys are in a tug of war. Which one's winning? The bottom's winning. Yeah, the bottom's winning, right? Okay, so it's bigger on bottom. So there's a horizontal asymptote at y equals 0 because exponent is bigger on bottom. So you're going to get a chance in the homework on my math lab to play with that and make sure you understand that rule. If you try one and you get it wrong, do those problems over and over and over again because it's going to be important for us, right? All right. How about, okay, here we go. Another example, f of x equals, and it's 3x squared minus 2x over 5x squared minus 4. Okay. Well, you're going to have to do, and it's going to be the same directions. Find any vertical or horizontal asymptotes. Okay. So for the vertical asymptotes, you're going to have to do the same thing we did before. We can't divide by 0. Okay. Solve for x, add the 4. Okay. Divide by 5, right? Because I'm trying to get that x squared by itself. So x squared is 4/5. And that's going to give me, because I'm going to square root both sides, I'm going to put in the plus or minus. X can't be plus or minus the square root of 4 over 5. Okay, so we got a different answer for our 2 vertical asymptotes here. 2 asymptotes, vertical. Okay, so that's that. What about, I'm not going to another page. I'm going to do it right here. What about the horizontal asymptote? Okay, remember, I don't care about those guys. I'm going to focus in there. The biggest term on top has an exponent of 2. The biggest term on bottom has an exponent of 2. So the exponents are the same. Right? So that is, take the y equals, take the coefficients right here and divide them. So I just basically say, hey, the x squareds are going to reduce out, and I'm going to be left over with 3/5. So that's an example of one where we have a horizontal asymptote and it's not a 0. Like the other one that we had was a 0. This one is not a 0. This one is, well, the last two we had was zeros. This one is y equals 3/5. So on a graph, that would be something like, let me show that real quickly. Y equals 3/5. Well, if this is y equals 1 up here, this is y equals 0, then 3/5 is going to be somewhere in there, right? Okay, so that is the kind of thing you're going to do. And again, you'd have pieces above, pieces below, just like we had before. So it works the same as if I had y equals 0. It's just that the horizontal asymptote has been shifted, basically. It's either above or below. Okay, so that's what's going on with that. Is that all right? Okay. Let's do one more of these. Let's just find the horizontal asymptote. Because it's kind of ugly. I don't want you to find the vertical asymptote. I'm not worried about that. So here's your example. I've got a couple that are kind of ugly. X to the third plus 4x squared plus 2x minus 10 over 8x to the fifth plus 5x to the fourth plus 3x to the third plus 2x minus 2x squared minus x plus 8. That's what I mean by ugly. It's not pretty. Okay. And no way am I going to ask you to solve for x in the bottom, figure out what your vertical asymptotes are, right? So it's just way too ugly. So I'm asking you for your horizontal asymptotes. This is those 3 rules. So you're basically going to go, I'm going to ignore all that stuff at the back. This guy has the biggest exponent on the top. And on bottom, this guy has the biggest exponent on the top, on the bottom. Remember, they might not always be in descending order, so make sure you look, figure out who really is the biggest. And so what we've got is f of x equals x to the third over 8x to the fifth. Those are the 2 guys that are fighting here, right? The other guys, they make it bounce around more, but they're not important. When we're looking at end behavior, end, E-N-D, behavior, these 2 leading terms, those are the ones that matter, right? So now look at your exponents. The top has a 3. The bottom has a 5. Which one's bigger? This is bigger on bottom, right? Y equals 0. Okay, that's your horizontal asymptote. Okay, so it really is a matter of just hone in on the 2 with the biggest exponents. There's one on top, there's one on bottom. They have the biggest exponents, and compare them. That's what you're doing. All right, one more. F of x equals 4x squared plus 2x cubed minus 10 over 8x cubed minus 7x plus 8. If you need to, pause the video and take a look. I hope that you're not fooled and you go, hey, that 2x to the third guy, he's out of order. He's the biggest, right? He has the biggest exponent. He's the one we care about. And then here, this 8x to the third, right? So if you pause the video, hopefully you saw that. Okay. Now I've got 2x to the third over 8x to the third. And what do we think about that? Look at your exponents. 3 on top, 3 on bottom. They are the same. Okay. So we do have a horizontal asymptote at y equals, and literally when they're the same, just think, oh, they can go away. I look at those coefficients and I divide them. So there's a horizontal asymptote at y equals 2 over 8, or I'm going to call it 1/4. Is that okay? 2 over 8 equals 1/4. Okay, just FYI. All right, so there you go. That's several examples of how you might see what's going on here differently with the horizontal asymptotes. You've got to practice those 3 rules and see what's happening with it. We're going to do a word problem or two here and make sure that we see the applications for it and why in the world am I dealing with this? Where's the business part of that going to come in? That kind of thing. So let's take a look. All right. This is straight out of your book. And there's an example that says there's a company that determines company determines that employee training influences how many computer components an employee can assemble. Okay, so how does this happen? Um, this is a company. They're trying to put together some parts for a computer. They need their employees to know what they're doing. Probably just Joe Schmo off the street doesn't know how to do that, right? Okay, so if I walk in there, if I personally walked into this room and they told me to, assemble these computer components, I'd just stare at them, right? I have 0 hours of training. I would be able to make 0 components. Okay. So that's not going to work for me. All right. You're going to have to train me and tell me what to do. Okay. So what happens is over time, this company comes up with a formula. Okay. A number of training hours, and it's a function. They've got it in function notation, and they say, here's the formula that goes with your training hours. Okay. N of T equals 50T over T plus 4. And they put a couple of little stipulations on it. First of all, they say T is the number of training days. Okay. And then they say T needs to be greater than or equal to 0. Okay. Why does T need to be greater than or equal to 0? Okay. If I walk in and I know nothing, okay, I have 0 days of training, then that's the minimum, right? Okay. So I can only go up from there as far as training and hopefully as far as numbers of computer parts I can put together, right? Is it possible for somebody to have a negative number of days of training? Like, hey, I trained for -6 days. No, it doesn't work that way, right? Okay. So that's why this needs to be positive, greater than or equal to 0, I should say, non-negative. Okay. T is the number of training days. So here's the question. And by the way, where did they get this? Some person in the management area, maybe an accountant or somebody in the finance area, or maybe just a supervisor on the floor of this particular manufacturing area, says, I've taken close notice and I've kept track. And if this guy got 5 days of training, then he was able to do that. If this woman got 10 days of training, they were able to do this many. The number of parts you can put together with this many days of training. Okay. So that's what somebody's taken care and put together a set of data. That's what this is. Okay. Which is pretty cool. That's a different kind of class, right? Okay, that's more on the business end of class. That's not on the math end of class. But somebody put this together and said, hey, we know that this formula represents our company. Okay. Now, the question is what? Why do we care? Well, whenever I bring in an employee, a brand new person, I want to know how many days they should train, right? So, in other words, is 1 day enough? Is 2 days enough? Should this person train for a week, 5 days solid? Okay. Assuming we're only working 5-day work weeks. Should this person train for 2 weeks? Okay. You have to think about it also, not only if this person's training, they're probably doing things slower, right? Because they don't know what they're doing yet. But I'm going to have a person off the assembly line showing them, or I'm going to have to send a supervisor over there or something, some kind of a trainer, right? So not only is the person being trained going slower, but the person doing the training is also going slower. So, while it might be true that 100 days of training gets me the fastest person alive, I might not want to spend 100 days training this person. I might not want to have a trainer available 100 days, right? So maybe we want to know, okay, when do we start approaching like a maximum, basically? And this is kind of a calculus idea. It lends itself towards a limit. Okay, if you've heard that term before, that's where we're headed. But it's a very calculus kind of idea of where's the optimal number of training days that I should be doing, and when do I stop seeing a positive return? Okay. When does this person just max out? Because, what do we have? 5 components made a day, 10 components made a day, 20 components. I don't know, but it would be nice to know where kind of the optimum number of training days is. So that's what we're looking at here. Okay. And the directions are going to say basically, let's find our isotopes and make a graph and see what we see. Okay. So here we go. Vertical isotopes for, remember this was my function. I had to change pages. I'm sorry. 50t over t plus 4. Okay. So I look at that guy and I go, let's talk about vertical isotopes. On the bottom, I am dividing, so I have to worry about that. Could take that guy out and say t plus 4 can't equal 0. Okay. I'm just going to subtract the 4. T can't equal -4. Okay. So number of days of training can't be -4, right? Well, that's an answer. And I only got one vertical isotope, right? So there's a vertical isotope at T equals -4. Okay. But we don't really care about that guy, right? Because what do we know about T? T has to be greater than or equal to 0, right? I can't have -4 training days. So it's a mathy answer that in this case doesn't really make sense in the real world. Okay. We do get an answer. T can't be -4, but it doesn't really pay off here because T has to be greater than or equal to 0. So we don't care. Okay. So let's keep going. Horizontal isotopes. Okay. Again, we're looking at this guy. Let me pull it apart. We don't care about this +4 guy. What we care about is the 50t on the top and the t on the bottom. Okay. What do we think about that? What are our exponents? T to the first here, t to the first there. When you compare those, what do you think? You think they're the same, Dr. Webster. Yes, they're the same. Okay. So if they're the same, we know we divide the coefficients. What's the coefficient here? There's an unwritten 1, right? Okay. So there is a horizontal isotope here at y equals 50 divided by 1, because those t's are going to go away, or 50. Hey, that's kind of a big horizontal isotope. We haven't had one big like that before. Okay. That kind of happens whenever you start doing these application problems and real world stuff, and you're like, hey, what's going on here? Well, we're going to have an asymptote, and sometimes they're pretty big, right? Okay. So let's look at this graph. Okay. And let's see what we got. One more time, I'm going to write this equation here so that I've got it. T plus 4, because we got rid of the plus 4 on that guy, right? Okay, so here's my equation. I'm going to graph it. We're going to have x's. I'm sorry, we're not going to have x's. We're going to have t's, and we're going to have n of t, right? Because that's my f of x or my y. Okay. So I have a vertical asymptote way over here at -4. We don't really care about him because he's not going to come into play. But I do care about this asymptote up here at y equals 50. He is definitely going to come into play because he's going to end up being a limiting factor here, which is important. Okay. I need a couple of points here because that's all I got, right? I don't have anything else. So let's figure out a couple of points. Um, I particularly like, for me, I like 0. What if I don't have any days? Okay. 50 times t, 50 times 0 is going to be 0. And then on bottom, 0 plus 4 is going to be 4, but we know 0 is 0. And I actually said this earlier, right? If I have no days of training, I'm probably not able to do this thing. I probably can't create computer components, right? It's probably not in my blood, so to speak, to just do that off with no training. Okay, so let's try n equals 1. We're going to do 1, and then we're going to do 10, because I think by the time we get to 10, we're going to see some stuff happening here. Okay, so n of 1 is 50 times 1 over 1 plus 4, right? Okay. 50 times 1 is just a 50 divided by 5. That's a 10. Okay. So let me go. I'm going to count here by tens. 10, 20, 30, 40, right? It's kind of a tight thing, but it'll be all right. So I've got the point. I put in t equals 1 day of training. I get out 10. So what does that tell me? After 1 day of training, if I went to this company, I would probably be able to make 10 components a day, right? That's pretty good. It's definitely better than 0. Okay. So for sure, the company should train their people at least 1 day, right? Okay. So that's good. What about the 10? I want to come out here to 10. 10 of 10. 50 times 10 over 10 plus 4. 50 times 10 is 500, right? 10 plus 4 is 14. Okay. Grab your calculator because I'm not doing that in my head. Okay. 500 divided by 14 is 35.72. Okay. 714. Okay. So it's about 35.7. Wow. Okay. 10 days of training. That's 2 full weeks, right? If you're doing 5-day work weeks. Okay. After 10 days of training, 2 weeks in this company, this person is able to make 35. So it's going to be right up here. 35 components. So if I'm this company and I'm trying to train some people to make me some computer components, yeah, I think it's probably worth it to do 10 days of training for sure, right? Because 10 days of training, this is a huge return, right? I'm doing well. The graph's going to look something like this. We see it going up. Again, it's being drawn to this asymptote like a magnet, but it's not going to go past it. So 10 days of training, that's looking pretty good to me, right? So we've got this point here, 10, and then it was 35.7. That's pretty good. Okay. So probably they for sure should train for 2 weeks. That's what it sounds like. But then somebody up in management starts going, well, we see so much better, right? After 10 days, this person's doing 35 components a day. Um, you know, should we train them more? Okay, so that's a legitimate business question. What would they do with 30 days of training? Maybe that's my question as the manager. Okay. At 30 days of training, stick in a 30, evaluate it, 50 times 30, divide by 30 plus 4, put it into the original function up here, right? 50 times 30, 30 plus 4, that is 1,500 over 34. Okay. And again, I'm not doing that math in my head. I'm going to use my calculator. 15, oops, push the wrong button. 1,500 divided by 34, 44.11. Maybe you could call that 12 if you wanted to, because the 7 would round up. Okay, so 44.12. Let's call it that. All right. So here we go. We had a huge jump here, right? From day 1 to day 10, this person is able to make 25 extra computer parts a day. Okay. But now we added 20 more days. We're way out here on this graph now, right? Okay. 20 more days of training, which you would think would be a lot, but how much did we add component wise? So 44 minus 35.7. Okay. Somebody in the office, the back office somewhere, is going to say, hey, we added 20 days of training, and this person can only do basically 8 and almost a half extra computer parts, right? So it's called diminishing returns. Okay. So I'm doing more and more training, but I'm not getting as big of a bang for my buck, right? Diminishing returns. Still, somebody might say, if they had that every single day for a year, that's 8.5 more components every day for a year. Maybe it's worth it. Okay. And then somebody says, it, we got to go there. Well, why don't we do 100 days worth of training? Okay. First of all, 100 days is more than 3 months of training. Okay. Companies just aren't going to do that. Just FYI. They're not going to spend that much time and energy training people, especially whenever sometimes this is kind of a transient population, right? Okay. But maybe you'd get that. Let's see. 50 times 100 divide by 100 plus 4, right? So this is 5, 3 zeros, 5,000 divided by 104. Sorry. 5,000 divided by 104. 48. Not even 48.1. We can round it, but 48. I'll round it. 48.1. The only reason I'm trying to round it is because I see that this one was a 44.1. Okay, so let's think about this. It was 30. We did 70 extra days of training, and basically we got 4 extra components a day out of these people. That's probably not worth it, right? Okay, so you might be able to convince somebody for 30 days of training, a month. It's really more than a month because it's 5-day weeks, right? So 30 days of training would be 6 weeks, month and a half. But you might be able to convince somebody of 30 days training, but you're probably not going to convince anybody of 100 days of training. And the real thing here is there's just a limitation, right? Okay, and that's why we see this asymptote up here. It's like a limit. Okay. There's really only so fast that I, as a human being, can do something, right? Even if I'm super fast and I'm trained and I know what I'm doing, like it still takes time to put those parts together, right? So this is 48 computer parts a day, okay, with 100 days of training. My limit here, or my horizontal asymptote, is 50, okay? At 100, I'm at 48. What does that tell you? 1,000? If I was way out here at 1,000, I'm getting close to 50. Am I going to cross that? No, because I'm in behavior now, right? I'm way out. I'm not in the middle here. I'm way out on the in behavior. So if you put in 1,000, and if you want to, just go ahead and put in 1,000 and see what you get. You're not going to get a number bigger than 50. Okay. So 1,000 days would be like, I don't know, 3 years, right? Okay. So this is already a third of a year, and I'm not even going to get bigger than 50, right? Because that's my asymptote. That's what's sucking me up to it. Excuse me. And I don't think anybody would ever be like, hey, let's have uh 3 years worth of training. That's just not going to work, right? Nobody's going to say that, but it's possible that they could say 30 days, right? So that's kind of the analysis that's going on in the back office, right? In the managerial areas. Okay, we want to train these people because if we don't train them, they're sitting around playing tiddlywinks, right? That's not helpful. Maybe they're thumb wrestling or something. Okay, that's not very helpful at all. But we can't overtrain them, right? And we can't spare somebody for that much time. So we have to say, hey, what's the optimal time for us? And basically, where are we going to get pretty close to 50? 50 is the max, basically. And maybe 10 days is good. Maybe they're happy with 35 units, almost 36 units a day. Maybe they want the 30 days of training for 44 units a day. We don't know. All right. So that's basically a really great way to think about conceptualizing the applications for this. Your horizontal isotopes, they're going to be limits. Okay. We're not going to really deal with limits in this class very much. If you've had a calculus class, I will very quickly go over limits when we get to the definition of the derivative, but it's just not that needed in this case. But it is a limit, and that's where we're looking at. That's a great example of what you're going to be doing with the business applications here. So that should prepare you well for the homework. And I am done. If you have questions, let me know, and have a great day.